Hello everyone, welcome back to lecture 7 part 2. So, we will continue the hyperspectral remote sensing data acquisition and processing. So, we were talking about the imaging spectroscopy. Now, let us understand how these absorption features are produced by a particular target, why they appear in our spectra, right. Then only we will be able to use them efficiently to characterize a material. So, here you can see this is one of the sample spectra, and here these absorption feature, as we understood, these are the characteristic absorption features of a given material, and these can be studied to say whether it is X, Y or Z material, right. So, what causes these absorption features? So, there are two general processes which produce this kind of characteristic absorption feature. First one is electronic and second one is vibrational. So, this electronic and vibrational processes are responsible for generating this kind of characteristic absorption feature for any given material or target, right. So, we will see one by one. So, let us start with the electronic processes. Electronic transition produces broad absorption feature that requires higher energy levels and occurs at shorter wavelength. So, when we talk about the electronic processes, one thing which is important to note, it is occurring at the shorter wavelength, right. So, this is at the shorter wavelength range. Now, here you have isolated atoms and ions which have discrete energy state, which is very clear from this, right. So, absorption of photons of a specific wavelength causes a change from one energy state to another energy state, right. So, what happens when there is a material, you have extra energy which is coming in the form of radiation or irradiance, which is falling on this particular material. And let us say here you have E1 energy level, right. Because of this extra energy, what will happen? This will change to E2. Now, this energy level of this material has changed from E1 to E2 because of some external energy, right. So, to maintain the equilibrium again with this surrounding, what will happen? This has to come down to E1 on its own energy state. So, this extra energy will be released and that will produce the characteristic absorption feature, right. So, here the emission of a photon occurs as a result of change in an energy state to a lower one and can be observed in the VNIR wavelength range. Now, when it is coming from E2 to E1, some extra energy which was present in the target, that will be released and that will occur in the shorter wavelength range. So, here we are having this at VNIR. When a photon is absorbed, it is usually not emitted at the same wavelength. So, when energy is absorbed by the target, it is released at the longer wavelength region. For example, it can cause heating of the material resulting in grey body emission at longer wavelengths. So, we talked about it earlier also. Now, let us see crystal field effects, that is the electronic, that is one of the electronic process. Common electronic process occurred in the mineral spectra due to unfilled electrons, cells of transition element like nickel, chromium, cobalt, iron, etc. The transition elements have identical energies in d orbitals in an isolated ions. The energy level is split when the atom is located in the crystal field. So, that is why we are calling it crystal field effects. Crystal field describes the breaking of orbital degeneracy in transition element complexes due to the presence of ligands or ions, right. Splitting of orbital energy state causes electron to move from a lower level into a higher one. Now, it is jumping from lower to higher one. The energy level are determined by the valence state of the atom, like whether it is Fe2 plus or Fe3 plus, its coordination number and its symmetry, right. The crystal field varies with crystal structure from mineral to mineral. Thus, the amount of splitting varies and the same ion like Fe2 plus produces different absorption positions, right. So, now you can see the Fe2 plus 3 plus both can be identified because of this crystal field effect. Now, here you can see this is one of the example reflectance spectra of two pyroxene showing the change in Fe2 plus absorption band position and shape with composition. So, here you can see the 1 micrometer versus 2 micrometer band position describes the pyroxene composition. So, here these two are the pyroxenes, right, and here because of the change in Fe2 plus absorption band position, the absorption positions are shifting or changing from one place to another place, which can be used to identify these two very precisely in the spectra. Now, this is the charge transfer, we also call it inter-element transition. The absorption of a photon causes an electron to move between ions or between ions and ligands. It can also occur between the same metal in different valence states such as between Fe2 plus and Fe3 plus. In general, absorption band caused by charge transfer are diagnostic of mineralogy. Their strength are typically 100 to thousands of times stronger than the crystal field transition. Now, what we mean by stronger here? Let us understand. We have one spectra which is having this kind of absorption feature. Now, we have another sample which has this kind of absorption feature. So, this is very strong compared to these two. So, when we talk about one particular material, the strength of charge transfer or inter-element transitions will be much more stronger than the crystal field transitions, right. So, here you can see the reflectance spectra of iron oxide hematite, iron oxide goethite. So, here you see how these two appear in the spectra. Now, let us talk about the conduction band. In some minerals, electrons may have two energy levels. One is conduction band, that is higher level. Here the electron moves freely throughout the lattice. Second one is the valence band, which is lower level. Electrons are attached to individual atoms. So, here they are moving freely throughout the lattice, here they are attached. So, this is valence bond and this is conduction bond, right. So, the difference between the energy level is called the band gap, occurs in visible region. So, here if you see any absorption feature in the 400 to 700 nanometer, right, and these are very characteristic and very clear. So, we call it band gap. So, we can find this conduction bands in 400 to 700 nanometer. This is one example. Here we have sulfur and cinnabar showing conduction band in the visible wavelength region. So, here these two are the visible region, right. Now, the color center, a few minerals shows color due to absorption by color centers. A color center is caused by irradiation, solar UV radiation. Crystal in nature have lattice defect which may produce discrete energy level. So, this is called color center. Because of the color center, you will also have the absorption feature in the visible and the VNIR wavelength region, right. Now, the second process is the vibrational processes, right. So, here the bond in a molecule or crystal lattice are like spring with attached weight, the whole system can vibrate. So, let us assume you have two masses attached to each other with this spring, right. Now, what happens if you hold one and just push little bit of this second mass, what will happen? These two will start vibrating, right. So, this can vibrate in this direction also or like this, because these are connected with a spring. The same way, the bond in a molecule crystal lattice are like spring with attached weight, where the whole system can vibrate and the direction can be seen here in this particular figure, right. The frequency of vibration depends on the strength of each spring and its masses. Now, let us assume you have one spring and here you have put a very small mass both side of it, and you try to vibrate it, you put some extra energy. So, this will vibrate and immediately it will stop. But if you attach a bigger mass here and you try to vibrate, this will not stop easily. It will take time to stop and then it can vibrate in all these directions, right. So, here you can see some of the vibrational processes. So, bending is possible. Here this is attached to these masses. Here this is symmetric, this is asymmetric. Here z axis rotation, y axis rotation, translation motion. So, with an animation I will try to show you how they appear. So, 3D animation of the symmetric stretching. This is symmetric stretching, here it is asymmetric stretching, scissoring, rocking, wagging. So, here you see how they vibrate. So, it is like a spring, and with this spring and the masses, how they are behaving, how they are vibrating. So, here this is the twisting, right. So, here you can see the rocking, it is very easy to understand with this animation. So, when we talk about the vibrational process, we talk about the fundamentals. So, the fundamentals can be identified using this concept. So, this is 3n minus 6 for a molecule with n atom. When we talk about the vibrational processes, the fundamentals are very important. It can be measured or it can be calculated using this 3n minus 6 for a molecule with n atom. So, n can be known, n can be identified, and then you can use in this and then you will get the fundamentals. Overtones and combinations occur at roughly multiples of the original fundamental. So, this is the fundamental. If a molecule has vibrational fundamentals at V1, V2, V3, then it can have overtone at approximately 2V1, 3V1 or 2V2 and combinations at approximately V1 plus V2, V2 plus V3, V1 plus V2 plus V3 or so on, right. Subtraction is also possible. So, like V1 plus V3 minus V2. So, all these are possible. So, we have fundamentals and overtones and then we have combination. So, these are roughly multiples of the original fundamentals. Overtone and combinations are 30 to 100 times weaker than the last, hence the feature will be more difficult to sense. The feature means the absorption feature will be very difficult to identify. Vibrational absorptions occur at longer wavelengths. So, this is SWIR and MIR, mid infrared. So, earlier we had the electronic processes which is in the visible and SWIR, right, and here we have this in SWIR to MIR. So, here we have deep and narrow features. So, that will help us to precisely identify the characteristic absorption feature. For example, the water molecule which is H2O has n is equal to 3. So, there are 3n minus 6, this remember 3n minus 6. So, here if we calculate this, it will be 3. So, 3 fundamental vibration will be available for water molecule. Now, here you can see we have calcite and dolomite. Comparison of calcite and dolomite spectra in MIR showing a small band shift due to change in the composition between the two minerals. Now, because of the change in the composition but very similar to each other, you can easily see how they are different, and it can be easily identified when we go for the spectroscopy, right. The level change calcite higher in reflectance than dolomite is because the calcite has a smaller grain size. So, if you want to go and learn more about this hyperspectral remote sensing and the basics, I will suggest you to read this imaging spectrometry and our paper, that hyperspectral remote sensing and geological application, which is available in the web. So, you can refer to them, is covering the very fundamentals of hyperspectral remote sensing. So, when we talk about the hyperspectral remote sensing, basically we are collecting the spectra and in the form of image. Now, we will continue this discussion. So, the collected spectra are the response of the material present in that particular pixel. I hope you learn how a particular characteristic absorption feature is produced by the material. So, it is basically because of the electronic and vibrational processes. Once we have the response of the material and that is getting captured by our sensor, so sensor is storing them into different pixels depending upon their position, and we will have the imaging spectrometry or spectroscopy, and we also call it hyperspectral remote sensing. So, the collected spectra are the response of the material present in that particular pixel. If spatial resolution is 1 by 1 kilometer, recorded reflectance is the average response of the material present within the field of view. So, when we talk about the satellite remote sensing, so satellite is here, we have one detector, for example, it is looking at the ground, right, and then it is covering this particular area, right. So, this particular area can be 30 by 30 meter, or it can be 1 by 1 kilometer, or it can be centimeter by centimeter level, right. So, depending upon the field coverage or the ground coverage, this whole area is getting captured, and the whatever energy is coming from this 30 by 30 meter is getting averaged, and you are storing them as one single DN value, right. So, if you have 30 meter by 30 meter, 1 kilometer by 1 kilometer, or 15 centimeter by 15 centimeter, you will have that much area covered at the ground level, right. So, if I am getting only one single value, we should have the smaller pixel size, because we are going to use this spectral information to identify the material. Now, can you imagine at the field scale, can you find one particular material present in 30 by 30 meter or 1 kilometer by 1 kilometer? It is very difficult. Sometimes we get, but sometimes what happen, you have different material present within the field of view, right. So, these many targets or objects will be present, and all of them are reflecting based on their chemical composition, and they are getting averaged, and that will be stored as one single DN value, right. So, in such situation, it is very difficult to identify the composition of the material present in the field of view of the satellite image, right, if it is in the meter level or kilometer level. Coarser spatial resolution introduces mixing of spectral signature within the field of view. I have a figure which can explain this particular concept. In nature, it is very difficult to find one type of object or material covering 1 kilometer by 1 kilometer, 90 by 90 meter or 30 by 30 meter. The effect of grain size and geometry are also significant in hyperspectral remote sensing data. Let us say I have A, B and C, 3 material, and my satellite is having 30 by 30 meter spatial resolution, right. So, let us say this is 1 pixel. Now, A is present like this and we also have D. A, B, C and D, they are present like this. Now, if we change the orientation, so this is A, B, C, D, this is also possible. Proportion will remain same, but the orientation, the geometry is changing here. That will also have some effect on the spectra. But remember, this will change the intensity of the spectra, but this will not change the position of the characteristic absorption feature, because materials are same, right. So, here we are talking about the grain size and geometry. And why this intensity is important? Because let us say if this is X and let us say this is Y. So, if these two are present in 1 pixel, let us say 50-50 X, Y, you will have the output reflectance spectra like this, right. So, all of them are present with the same strength, the absorption feature, because this is one line 0 to 1 reflectance, and from here we will see how much absorption is happening here, and this we will calculate the area under the curve, right. And then we will say how much X is present, how much Y is present. So, in such situation, this grain size geometry will also play a critical role. So, the spatial resolution is very important and very critical when we talk about the hyperspectral remote sensing data analysis, right, because 1 pixel is producing this kind of a spectra which is representing a bigger area on the ground, and in that particular field of view it is very hard to find one type of material. So, it can be a mixture of material. So, when we talk about the ideal condition, right. So, in ideal condition, let us assume that we have one particular target which is available in, let us say 30 by 30 meter or 1 kilometer by 1 kilometer. Now, we are having this source and which is illuminating this, and it is getting reflected or emitted, emission will be measured here. So, the collected spectra are the response of the material present in that pixel. In this example, I have used only one type of object of material within the field of view of this particular sensor, right. So, in such situation it is very easy, you will get only a spectra which is representing quartz, right. But in another condition or the natural condition, this is the scenario where 1 pixel is having so many object or material and they are available in different orientation and geometry. So, what will happen? In such situation, you will find this kind of a spectra, and this will be mixture of all X, Y, Z, A, B, right. So, this is the problem with hyperspectral remote sensing, that 1 pixel representing the ground is actually large and one type of material is not present within meter or kilometer level. Because of that, you are having the non-linear mixing problem. So, here you see, if my material is present in such a way, X, Y, Z, A, B all are present here, So, you are getting a spectra, right. So, you can do this, you can give weightage depending upon the area, and then you will get this kind of spectra. But when you have the non-linear combination of all these material present within the field of view, then what kind of spectra you are getting? So, that is very hard to interpret and hard to quantify. So, what we do is, we assume in hyperspectral remote sensing data analysis that the material present within the field of view of my sensor are linearly mixed, right. So, we try to avoid this non-linear unmixing, we try to go with the linear unmixing problem, right. And this linear unmixing will give you the combination of all these material present within the field of view, and then you can quantify their composition, you can quantify their presence in the pixel. So, let us talk about the spectral mixture analysis. How do we do it? So, let us assume that you have identified a particular mineral, let us say this is quartz, with the conventional method. Right. So, you go with XRD and then you can say that this is a quartz, right. Now, once we have this quartz which is also present within the field of view of my image, right. So, this is 1 pixel. So, 50% is quartz and 50% is mica. So, now we have also identified mica through the conventional techniques, right. Now, we are very sure that this particular study area and this particular location has 50% quartz and 50% mica, right. Now, we go to the field, we collect the quartz sample from here, we collect the mica sample from here, we analyze them and we confirm whether it is quartz or mica. Then, based on the satellite data, we will see in which particular pixel it is coming, and then we will see whether it is 50%. This is just to understand the concept. Now, once you have that, then you have a spectroradiometer. With a spectroradiometer, you will produce one spectra for the quartz, one spectra for the mica, right. Now, if it is 50%, I can just simply do this in Excel itself. In Excel, we will have this is wavelength, this is quartz, this is mica, right. And then this is the pixel spectra, let us say. So, this is lambda 1, let us say this is R1, this is RM1, this is R2, this is RM2, this is lambda 2, right. Now, we know that this particular pixel has 50% of quartz, 50% mica. So, I can simply do this R1 into 0.5 plus RM1 into 0.5, right. So, like that you will produce the combination of these two spectra which is representing this particular image, right. So, this kind of analysis we have to do when we talk about the spectral mixture analysis. So, we have almost characterized all type of minerals, rocks which are present, even the soils, all the materials. We have the spectral measurement cap. Now, there are few libraries available from different sources which has different minerals, rock and soil spectra that can be considered in the spectral mixture analysis. So, identification of pure minerals through field investigation or conventional techniques, measurement of representative spectral signature of mineral or pure materials, Sometimes a single material feature object can exist in several forms due to change in the composition or state, which results in different spectral signature. Then we go for the spectral library. SMA is a technique to determine the proportion of different feature of known material object. SMA uses the spectra of known material from the spectral library. So, here when we talk about the pure spectra of a particular material, let us say if we collect the spectra of pure quartz, we will call it, this is the true representation of a quartz, right. So, then we can call it end member. So, this is the spectral end member are the pure spectra that are used as a reference to deconvolve the measured spectra into known material. End members can be said as pure spectra for a specific image or a specific area for a specific target. They are the purest pixel in that particular image. So, what we do is, in the image itself we also have to identify which are the pixels covering one type of material on the ground, and their response, their spectra will be considered as pure spectra, and we also call it end member, right. So, difficulties in selecting the end member. Sometimes the end member cluster is not present in an image larger than the pixel size because of the spatial resolution. End members are not truly constant in an image and sometimes create a mismatch between the defined end member and its actual form on the ground. Non-linearity due to shadow. Because of this shadow you will have some additional information in this spectra, and that will be confusion while selecting that particular pixel as an end member. Sometimes inherent variability in nature like rain, growing cycle phases, etc. makes it difficult to match end member with actual pixel composition. So, these are some of the practical problems. Now, assumption in estimating each image pixel composition. Each pixel contains information about the proportion and spectral response of each component. Brightness, which can be your DN value or radiance or reflectance, which is captured by the sensor of an image pixel, is a linear combination of the percentage of each end member and the brightness of the pure sample of that end member, right. Spectral proportion of the end member shows the proportion of the area covered by feature on the ground. Most of the pixel contains some measurable amount of the end member. So, these end members are not very easy to identify, because in nature one pixel what we are capturing from the space in 30-meter spatial resolution or 90-meter or 1 kilometer spatial resolution, it will be very hard for us to identify a single material present within the field of view. So, that is why we have to very rigorously find a pixel which is having a representation of one type of material or object. So, when we go for the spectral mixture analysis, so we have one spectra from the image which is unknown, we do not know the composition, but we should have some sort of information from the field that what kind of minerals or rocks or soils are present in that area. Accordingly, the standard measured spectra by some other agencies or people that can be used here as a reference, right. So, the library spectra are the pure spectra of, let us say, quartz, mica, feldspar, or maybe any standard material, right. And we are expecting that my pixel will have the combination of these 1, 2, 3, 4, 5, 10 materials. So, those will be available, or I should collect those information from different spectral library. Then different combination of spectral library will be generated. So, let us say I have X, Y, Z, A, B, C, D. These are the material which I am expecting to present in my study area, right. So, what I will do, I will generate the linear combination of these materials. So, first we will go with 1% of X plus 1% of Y plus 1% of Z plus, like that we will go and we will complete it to 100%, right. Then we will change these values, these weightage, and then you will have that many combination, and then we will try to match it with the pixel spectra, how they are matching or how well they are representing this absorption feature, right. So, that is how the spectral mixture analysis is done. So, with this we will be able to say that this particular pixel has A, B, C or D, E, F or G, E, F material, right. So, this library will be generated with this spectroradiometer. As I mentioned before, there are pure spectra which are measured by different agencies are available, and that can be used here as your library spectra. For that we are taking the help of spectroradiometer. Now, it is very important to note that when you are generating the spectra for the library, you should take care of the spectral range, spectral sampling and number of the spectral bands which are measured here and from the space, because here we are having the measurement at 0.1 nanometer, right, and here you are having the 10 to 20 nanometer interval. So, you have to take care of this number of spectral band, number of sampling, number of or spectral range. So, let us say here it is from 350 to 2500, here it is 400 to 2500. So, you have to match this spectral range, you have to match the spectral sampling, right, and then once you do that, the number of spectral band will be equal for both the measurement. Then these two can be used here, and then this spectral analysis can be done. So, when we talk about the hyperspectral data analysis, when we talk about the analysis of the hypercube or the satellite hyperspectral data, this is the flow that we have to follow. So, initially we have to convert the dN to radiance and radiance to reflectance. Then we have to go for the minimum noise fraction to identify the inherent data property, which are the unique information measured by our sensor. The additional information which is repeated, so data redundancy will be removed as well as the noises will be removed. Then we use this end member which can be from your spectroradiometer. If you have a spectroradiometer, then you go with this. If you do not have, then from the image itself you have to derive the end member, and here you will follow this pixel purity index, and then from there you will do the end member selection. Once you have the end member, doesn't matter whether it is from image or from instrument, that can be used together to go for the mapping of a specific material or classifying the image. Once you have the end member from image or library, right, that can be used further to analyze the hyperspectral remote sensing data, and then further you will classify this hyperspectral data and you will come up with the different classes or categories which is representing mineral, rocks or soil, or maybe different types of land use, land cover, or different types of man-made material present in that particular study area. So, with this I will end this lecture and we will continue this course with lecture 8. Thank you very much.